swear to God. Okay, so we're starting a brand new topic. How could we solve quadratics in the form ax squared equals c? So the last topic we were talking about solving quadratic equations by factoring. This topic will mention factoring a lot. However, we're going to first start looking at equations that may not be factorable. So how could we solve equations in the form ax squared equals c? So normally when we talk about a quadratic equation, I'm going to look down here at ax squared plus bx plus c equals 0. But today's equations we're going to look at are sometimes referred to as incomplete quadratics because they're missing the b term, which means that b is equal to 0. So the do now just says, can you name a value or values of x that would make each of the equations true? So the first one, what number squared is equal to 4? Well, everyone's going to think of 2, but there's actually another number that if you square, it's going to equal 4, and that's negative 2. Positive 2 times itself is 4. Negative 2 times itself is 4. X squared equals 1. Well, if x was 1, 1 squared is equal to 1, and negative 1 squared is equal to 1. So for 9, by now, you should realize that it's not only positive 3, but it's negative 3 also. X squared equals 25, so x could either be positive or negative 5. And the same for the last one. If x squared equals 100, x could either be positive or negative 10. So we have nice rational solutions because each of these had x squared set equal to a perfect square. And in that case, or any time you have x squared equal to a number, you're always going to be able to square the positive or negative of the square root. So again, the definition of a quadratic equation, you have to have a variable with a degree of 2, the highest exponent being 2. That's the definition of a quadratic equation. Its general form is ax squared plus bx plus c equals 0, with a, b, and c being constants or numerical coefficients, and x is an unknown variable. The only rule is that a can't equal 0, because if a were equal to 0, our quadratic term, our x squared term, would be gone. But b could equal 0 because this x term can disappear. So given the list of equations below, circle the ones that are quadratic. So let's look through them. The first option here, we have the x, but it's not squared. So this is actually a linear equation. The next one has x squared, so I'm going to circle it. The next one, it has an x and a fraction, so maybe we want to get rid of the fraction to see what it would look like. I could put 10 over 1 and cross multiply. It would give me x is equal to 60. No x squared in this equation. 4x squared, so this one is quadratic. It has a quadratic term. X cubed equals 8. No, actually, that's a cubic equation because it has an x cubed. You want the highest exponent to be 2, like in this next one. 5x equals 13. That's a first degree equation. There's no x squared. The next one, I don't see an x squared, but I could simplify with the parentheses by distributing, which would give me x squared plus x equals 4. So that is a quadratic equation because there's an x squared. The next one has 2 terms with an x in it, but if I combine those, I'll actually get 3x plus 6 equals 5. That's a linear equation, so I'm going to cross that one out. The next one, if I cross multiply, I'd get x times x is x squared equals 36. That's a quadratic equation because it's a second degree. The next one's first degree, so it's linear. And the last one also, nothing squared, it's linear. So there were 5 equations that we circled. Some easier quadratics to solve are called incomplete quadratics, like the ones given earlier. These quadratics are in the form ax squared equals c. They are missing the bx term because b is equal to 0. So today is going to be very simple. I will do the first set of examples here. When they just give you x squared is equal to a number, you could solve it by just taking the square root of each side. However, x squared has to be by itself. So all 4 of these examples, the x squared is isolated. And when I take the square root of both sides, it's just extremely important that you remember that it's not just positive 6 that will make this equation true, but negative 6 also. A second degree equation should have two solutions. When I take the square root of both sides here, x is equal to positive and negative 9. When I take the square root of each side here, I get that x is equal to positive and negative 4. When I take the square root of x squared on both sides here, I get x is equal to positive or negative the square root of 1/4, which is 1 over 2, because the square root of 1 is 1 and the square root of 4 is 2. So again, these all had rational solutions because everything was a perfect square. For incomplete quadratics, we can simplify, use the inverse of squaring, which is to take the, what did we do? We took the square root. This allows us to isolate x, get the variable alone, which has always been the goal when solving an equation. Please don't forget to include both the positive and negative solution. So a lot of times we're going to say in this topic, positive, negative. Anytime you're taking the square root to solve a quadratic equation, you need to remember plus or minus, positive or negative. There are two reasons we must have two solutions. The first reason is what we discussed in the do now. A positive and a negative number squared will always give you the same solution. The second reason is if the degree or highest exponent is 2, there will be two solutions. So every time you're solving a quadratic equation, you will end with two solutions. Now this next set of problems, we're going to discuss that you can choose to use factoring like we did before. When the solutions are rational only. No, Smith. When the solutions are rational, you always have the option of factoring. However, sometimes the solutions aren't going to be rational. So you could look at this model problem here, just like everything we did last topic. Before you could factor, you have to set the equation equal to 0. Factor, in this case, if it's an incomplete and it's missing that b term, that means it's going to be the difference of two perfect squares. You'll tee it up and then solve. So in the next section it says you could do it either way. I'll do the first one, this reminding you that you can do it using factoring. So subtracting 121 from both sides, I get x squared minus 121 equals 0. So now that it's set equal to 0, you could solve. This is a difference of two perfect squares, so I'll get the square root of each. So my factors are x plus 11 and x minus 11 equal to 0. So then I will tee it up, set each factor equal to 0, and again, you're still going to get the positive and negative value, negative and positive 11. So you could choose to use that for any of your homework problems, or if x squared is by itself, you could just take the square root of both sides, but you have to remember positive or negative square root of 49, which is 7. So if you don't do that for the worksheet, I'm going to keep writing. Don't forget positive, negative. Don't forget positive, negative. Here, don't forget positive, negative. X is equal to the positive or negative square root of 1/9, which is the square root of 1 over the square root of 9, which is 1/3. And lastly, also of the examples we have solved involve numbers that are all perfect squares, which are rational numbers, numbers that stop or repeat. We could also solve using square roots for problems that have non-perfect square roots that are irrational numbers. Take a look at the question on example 4. The types of problems below will not be factorable if you get them equal to 0. So any quadratic equation that's not factorable means that the solutions are going to be irrational. So this is what it'll look like. For A, I'll take the square root of both sides just like all the others, but the square root of x, I will still get a positive and a negative solution, but I can't get the square root of 10. If I put it in the calculator, Smith, enough. If I put it in the calculator, I will get a non-repeating, non-terminating decimal. So I'm just going to keep it square root of 10. Done. Okay, same with the next one. If I take the square root of both sides, I get x by itself. I get the positive and negative solution. But if I take the square root of 7, it's a non-repeating, non-terminating decimal, so I just leave it in radical form. And the square root here of both sides, I isolated the x. I get the positive and negative answer, but you cannot take the square root of 2 without getting a non-repeating, non-terminating decimal, so I just leave it the square root of 2. So these last three equations had irrational solutions, so they're square roots in the answers. All the ones before that, like in this section here with example 3, the solutions are rational. There's no square root in your answer. So I'm going to leave you with just remembering that anytime you take the square root of both sides of a quadratic equation to solve, not to forget to take the positive and negative solution.